Hello students, welcome back. Today we step into one of the most powerful ideas of calculus, the fundamental theorem of calculus. Now here's something to think about. When we talk about finding the area under a curve, it feels like pure geometry. But what if I told you that the rate of change of that area is exactly the height of the curve itself? That magical connection is what this theorem establishes. We start with a definite integral. Integral from a to b of f of x dx represents the area bounded by the curve y equals f of x, the vertical lines x equals a and x equals b, and the x-axis. But what if instead of fixing b, we let the upper limit vary with x? That gives us something new, the area function. Formally, if f of x is greater than 0 on the interval from a to b, then for each x in this interval we define a of x as integral from a to x of f of t dt. So a of x equals integral from a to x f of t dt. This means a of x gives the area of the region bounded by the curve y equals f of t, the vertical lines x equals a and x equals current x, and the x-axis. In the NCERT figure, this is exactly the light shaded region from a to x under the curve. Now, let's talk about the nature of this function a of x first. If f of x is continuous on a, b, then a of x is also continuous. Second, if f of x is always greater than or equal to 0, then a of x can only increase as x increases. It is a non-decreasing function. Third, at the starting point, a of a equals 0 because integral from a to a f of t dt equals 0. And finally, as x increases from a to b, a of x represents the cumulative area, growing larger as more of the curve is included. Here comes the heart of the concept, the fundamental theorem of calculus. It states that the derivative of the area function a of x is equal to the original function f of x, symbolically, a dash of x equals f of x. This is huge. It shows that differentiation and integration are inverse processes of each other. Think of it like this. As you slide the vertical line to the right, the area increases. The rate at which this area grows is exactly the height of the curve at that point. Geometry and calculus shake hands beautifully here. Let's confirm this idea with an example. Suppose f of x equals 2x and we define the area function from 0 to x. So a of x equals integral from 0 to x of 2t dt. When we compute, it becomes t squared evaluated from 0 to x, that is, a of x equals x squared. Now differentiate. Derivative of x squared is 2x, which is exactly f of x. This proves the theorem perfectly for this case. You can literally see it. Under the line y equals 2x, the area forms a triangle whose area is x squared and its rate of growth equals the line's height. This theorem is not just a theoretical beauty, it's extremely practical. It allows us to compute definite integrals easily using antiderivatives. It also cements the connection between differentiation and integration to central operations of calculus. And it provides the backbone for real-world applications, calculating displacement from velocity, work done from force, probabilities from density functions, and much more. So whenever you see a definite integral in action, remember that the fundamental theorem of calculus is silently at work behind the scenes. So let's wrap up. We define the area function a of x as integral from a to x f of t dt. We saw that a of x is continuous, non-decreasing if f of x is non-negative, and satisfies a of a equals 0. The core result is the fundamental theorem of calculus. Derivative of a of x equals f of x. This means integration and differentiation are inverse to each other. And that's the foundation of the area function and the fundamental theorem of calculus. In the next video, We will explore how to use this theorem to evaluate more complex definite integrals with confidence.